Hello. So last time we learned how to solve the heat equation for a specific scenario, which was through separation of variables. And now we're going to learn how to take that solution and generalize it to any initial conditions that we want. Cool. So just to review what we went through yesterday, let's imagine. So we have our partial differential equation, partial u over partial t is equal to negative k partial squared u over partial x squared. And we found that a solution to this equation is u equals b times sine n pi over L times x times e to the minus n squared pi squared over L squared, or e to the minus k times n squared pi squared over L squared t. Great. So the first thing I want to show is that this solution is generalizable because we can now we can say that any solution to the heat equation can be rewritten as a sum or as a linear combination of this original solution, right? The sum as from a linear combination of this solution, b sub n of, let's copy paste, right? The reason we can say this is that the heat equation is what we call linear. That is, if I rewrite this equation as partial u over partial t plus k partial squared u over partial x squared equals 0, you'll note that we can kind of think as partial over partial t plus k times partial squared over partial x squared as some kind of operator x that operates on x, giving us 0. And so in this case, or sorry, not on x, on u, giving us 0. And so then we can think of u as a null space. And therefore, because it's a vector space, you must be able to use vectors in that space and take linear combinations as we do here to get any vector in that space, or in other words, any solution. And so if we can describe any solution as a sum of this sine exponential term, we can then describe any initial condition, u of x comma 0, as the sum of a bunch of sines. Because, if you plug in t to here, then this becomes 1, and you're just left with the sum from n equals 1 to infinity of b sub n sine of n pi over L x. This is kind of a crazy equation because it's basically saying that you can describe any function, any continuous function, or any function for the most part as a sum of sines, which is kind of weird to think about. And this is the whole basis for Fourier series. Kind of like how you can describe any function as a series of polynomials with Taylor series. Cool. So now the question becomes, and actually one more thing I want to prove. So as I showed up here, we can clearly see that this forms a vector space, the solution space. We can call it solution space of the heat equation. It's a vector space. One more thing I want to do to kind of prove this point is by showing the orthogonality of sine of this term sine of n pi over Lx. What I mean by that is that for this term to be used as a basis vector, we need to show that for all sines of all numbers n from 1 to infinity, that they're all orthogonal to each other and therefore form an orthogonal basis space. And the way I want to prove that is by showing that, so the way that you would normally prove that two vectors are orthogonal is you would take their dot product. V dot W equals 0 means that they're orthogonal. And what you'll notice is that if we do a similar thing here, instead of taking the dot product, though, taking the integral of the product of, say, a sine of n pi over L times x times sine of m pi over L times x, if with respect to dx, which is kind of equivalent to the dot product we're talking about here, you'll note that if you solve this out, for where n does not equal m, this equals 0, as to be expected. But where they are equal, where these two vectors are the same, we see that it's equal to L over 2, which is just more proof that shows how this is just a vector. The solutions to the heat equation is just a vector space. And so now the question becomes, how do we figure out the coefficients B? And the way to do that is through kind of a long and a little tedious derivation, but we'll go through it. So, as we said in the previous line, I'll copy paste it. U of x comma 0, the initial condition, is equal to a summation of coefficient times sine of n pi over Lx. Now let's multiply both sides by some arbitrary sine of m pi over Lx. And then I'll just copy paste this. And then multiply this side also by that term. And then let's also take the integral of both sides with respect to x. And you can see how this integral trick from before over here is kind of coming into play. Well, then we see and from 0 to L, like the same bounds as the below. Well, then this side stays as is. But this side we can rearrange to be, because these aren't dependent on x, we can take the sum out and the b out, b sub n. And so we're left with the integral from 0 to L of sine of n pi over Lx times sine of m pi over Lx. And what's kind of cool is that, hey, this looks a lot like what we derived over here. And so we can say that for any values where n does not equal m, well, we can't, b sub n is equal to 0, and we can't come up with a value for b sub n because it's 0. But when n equals m, then we can say that the integral from 0 through L of sine, here, wait, hold up. Integral of sine of m pi over Lx times the initial condition times d of x is equal to b sub n times L over 2, because everywhere else it's 0, right? It's plus b sub m, b sub n times 0 plus b sub n plus 1 times 0, etc., etc. So this is the only place where b actually has a value. And so we can now say b sub m is equal to 2 over L times the integral from 0 through L of sine m pi over Lx times the initial condition with respect to x. And then we can just solve this integral for every single value of m to as many degrees of approximation as we need. So if we need to get 4 degrees of approximation for this Fourier series to approximate the function, we can do 4 from 1, 2, 3, 4. And similarly, if we want even higher degrees of approximation, although to get the actual value of the actual function to get the actual function that we need to calculate all infinite values of b, which is an infinite series. But yeah, we can use this formula to get generalized solutions. And to show an example of this, let's do a problem. Let's say we have a rod, like we've had this whole time, and this time its temperature is not just a sinusoid function, because we know how to solve the heat equation for initial condition of sinusoid. But let's say that the initial condition ux comma 0 is equal to 100 for 0 is less than x is less than L. Let's then say, just to keep things simple, as we did previously, that u at 0 comma t, the boundary condition, is equal to 0. So it would just drop down. And similarly at L, it would drop down so that u of L comma t also equals 0. And again, we know our heat equation is partial squared partial x over partial u over partial t equals minus k partial squared u over partial x squared. Now, we can solve this equation. And the way we do that is we can, using what we had before, we now know that u is equal to the sum from n equals 1 to infinity of b sub n sine of n pi over L times x times e to the minus k n squared pi squared over L squared times time. And now we need to solve for b. Well, using the formula we came up with, we know that b at a given m is equal to 2 over L times the integral of sine from 0 to L of sine of m pi over L times x times the initial condition function, which is 100. Keeping it simple with respect to dx. Now, solving this, we get b sub m is equal to 200 over L times, times L over m pi cosine minus cosine, of m pi over L times x. And this is all from 0 to L. Then plugging that in, we get b sub m is equal to 200 over L. And I guess these L are, we'll get there. And I guess these L's cancel out. So we can say 200 over m pi times 1 minus because if we plug in 0, this becomes cosine of 0, which is 1, and L, which is sorry, minus 1. M pi cosine of M pi minus 1. Except, wait, sorry, but the other way around. 1 minus cosine of M pi. And what we can further do is now we can say that B sub M, we can actually notice that for any value of M that's even, this value becomes 0. And for any value where M is odd, it becomes 400 over M pi because cosine becomes 0. When N is odd, and when N is even, this value is 0. And we can incorporate that into our initial solution, initial value, and we can say U is equal to the square, or sorry, is equal to the sum from N equals 1 to infinity of 400 over N pi over N pi sine of N pi L over L here. Where, of course, as we mentioned here, where N is odd, such that N is odd. And now we have a complete equation. And actually, if you were to plug this into Desmos or some kind of graphing software, you'll see that, well, for N equals 0, it'll look like this. But then for N equals 1, it'll look like sine of pi over L x. And we can see that over time evolution, it will slowly start to asymptote or to decay to 0. And so you can actually use this approximate. This is now the complete solution for our heat equation problem that we have up here with the initial conditions that we gave. And now you can use the Fourier series combined with separation of variables to get the solution to the heat equation for any initial conditions.